Hi, welcome to the third live session of quantity topology 2 course. My name is Shautik, and right now I'm doing a research at IIM Madras under Total Scholarship. So, today's in this live session, we shall first go through compactness, separation axioms, and we shall solve some problems. Then we shall go for local compactness, and then if time permits, then today we also go for partial fusion. Okay. Okay. So let's start with basic problems and then gradually this to continue. Okay. First, try to solve some problems that are compact. So, so so first question is, show that the closed interval 0, 1 is not compact as subspace of R. So, yeah. So the question, they want to show the closed interval 0, 1 is not compact as a subspace of R. Okay. So how to do it? I mean, so basically what we need to check, we need to find an open cover which does not have a finite structure, right? Now observe that this set 1 by n comma 1 by n plus 1, sorry, union minus 1 comma minus k union half comma 3 by 2. This is then open power of R surface, right? But if here this open power U has, so now it's quite obvious, because if the finite subcover consists of the terms, sorry, yeah, so if these are the finite elements in the cover, union these two obvious things, and suppose this is strictly increasing, then uh, then for any n which is strictly greater than nk plus 1, this element 1 by n does not belong to that open interval, right? So this n plus u has no finite subpower. So that's a closed one is not a compact space. I mean, not a compact subspace of R R suffix R plus one. So these are just hold on. Audible. Hello.
Yes, sir.
And can you see the screen?
Yes, sir.
So yeah. So the first question is that closed 01 is not compact as a subspace of R topology. Okay. So by the way, can you recall the definition of R with K topology?
Sir, it has a basis of the interval AB in which we remove the set K of
Yes,
the set K.
correct. So we need to check that closed 01 is compact. So basically, we need to find an open cover of closed 01 which does not have a finite subcover. Okay. So first we choose the open cover U to be the all those open intervals 1 by n plus 1 comma 1 by n union minus 1 upon minus k, and I mean yeah, this 0 belongs to this portion and union half comma 3 by 2. This contains 1. Now we claim that U has no finite subcover, because if U has finite subcover, then I mean this 1 by n plus 1 1 by n, this will only have finite many n's which cover the whole U. And suppose nk are strictly increasing order, then if we take any natural number n which is greater than nk plus 1, then that natural number will not lie inside these open intervals, right? So that's why this U has no finite subcover. So this is the argument. Let's go through the argument and let me know if you understand the argument or not. Don't hesitate. Just try to understand the argument and let me know whether you understand the argument.
Sir, the cover which we defined is the union of 1 by n plus 1 and 1 by n and union of the minus 1 to 1.
Yes, minus k, minus,
Huh.
and union of half comma 3 by
Sir, 1 is belongs to the set. Yeah, belong.
sorry.
Uh,
No,
Sir,
no, I
we
mean,
are assuming.
this open interval does not contain one, right?
What's the first one is containing 1?
Uh,
1 by n.
no, first element is what? Half comma 1, right? So 1, the 1 is
Oh,
not,
yes, sir. Yes, sir. Yes, sir. Got it.
Also, do you have any doubt or any questions? You can ask. So, okay, so can you, so do you know the limit point compactness, right?
Yes, sir.
So, definitely you know that compactness implies limit point compactness, right?
Sir, in metriable space.
Okay. Yes, but in topological spaces also, topological space also compactness implies limit point compactness. Do you know about this?
Yes, sir.
Okay. So, what about the converse? I mean, can you give an example for the limited compactness does not imply compactness? Can you give one example? Think about it. Think about it.
Sir, if we take the first example with K topology,
Okay.
0, 1 is an infinite subset,
Yes.
but the limit point
Tell out. Yeah, complete the argument.
uh, sir, it is not compact.
Yes, it is not compact, but I mean, the thing is, this set, I mean, this set is already closed in R3. Okay, this is already closed in R3, right? Because this is closed in usual topology, right?
Yes, sir.
It is already closed. So, one, one contract will be considered this space n cross 0, 1, and take this, I mean, take this 0, 1 with a discrete topology. Okay. Then under the product topology, this space is limit point compact. Sorry, here you need to consider the double tone 0, 1 within discrete topology. Double tone 0, not the double tone 0. Okay. So the point is that n cross double tone 0, 1 and double tone 0 constitute indiscrete topology. Under that thing, n cross double tone 0, 1 is limit point compact on the product topology. But obviously it is not compact. Now try to realize that why n cross double tone 0, 1 is limit point compact. Do you understand the point?
Sir, N has also indiscrete topology.
No, no. N has all n with discrete topology, but double tone 0, 1 with indiscrete topology. I mean n with discrete. in the usual, and double term 0 1 in this case, of course. So I realize that under product over this space is limit point compact.
Sir, if we take infinite subset A cross B, so where B is a subset of 0, 1, then the either it will be singleton 0, 1 or the whole space, and if it is for the limit point belongs to B, then the only open set are empty set and the whole space.
Yes, yes, correct.
So if it take any subset, then the limit belongs to be that.
Yes. I mean, so basically, since 0, third order 0, 1 open set containing both 0 and 1, so any point will be the limit point basically, right? So you're always right. So yeah, so this is space a limited compact, but it is not compact. So now can you think why it is not compact? I mean, you need to find an open cover, and it is almost easy. But just tell me the which open cover you will take. That's the point.
Sir, if we take cover for this space, so for n it will be all the subset of n, and uh, for 0, 1 itself 0, 1 is the yeah or impartition. So if it has a finite subcover,
No, no, yes. Can you repeat the cover? Which is the cover is it?
uh, sir, Uh, I am taking the covers are of the form the all the subset of n
Uh,
into the space 0, 1.
yes.
Then it has a finite subcover, so it contradicts because n is a infinite.
Yes. I mean, you told that all possible subsets of n exist, right? But only singleton n where n belongs to, and for each n, if you consider this, then this also forms a cover. So this will not a finite subcover, right? I mean, anyway, your argument is correct. So, do you know about local compactness? Know about local compactness? Please tell me. Do you know about local?
Compacts are compact neighborhood at each point.
Sorry, can you please repeat?
So compact neighborhood at each point. If we take any point, so an open set, there is a compact subspace which is contained in open set.
Okay. And do you know one point compactification?
Yes, sir. I read it, but I did not remember.
And can you remember the gist of the one-way compactification? Not the technical detail, just the gist. What does it actually do? The one-way compactification. Can you just tell? Okay, so let's start with the one-way compactification. Okay, before starting, just let me know, do you have any question or any doubts before the previous, uh, from the previous live session or anything related to this syllabus? Do you have any doubt, any confusions? If yes, then please ask. So, what does this one-way computation? So, if Y is a compact housed of space and X is a proper subspace of Y, such that whose closure is Y, then then Y is said to be compactification of X. And if Y minus X is singleton set, then Y is said to be one point compactification. So this is the definition. Okay, and after that there is a one theorem which I'm not just going to prove it. Uh, Sir has proved it, or maybe you can get in any standard. The theorem is that, I mean, okay, so in the definition of one-way computation is, you have seen that, so these are definition of one computation. Okay, now we have a theorem which tells that under a certain condition, one-point computation of a space exists. Okay, that's the theorem. So let X be a space, then X locally compact house dot if and only if there exists a Y such that Y contains X as subspace, uh, Y is compact construct, and Y minus X singleton. So this is the theorem which tells that Y locally compact house dot if and only such a thing holds. Okay. So and this tells, and so Y is a one point compactification, and also there is along with this theorem tells that such a Y is unique. So this is the theorem that X is space, then Y is locally compact house dot if and only there exists a Y such that X is contained in Y as a subspace of Y. Secondly, Y is compact house dot. Thirdly, Y minus singleton. And also this theorem tells that this such a Y is unique, and this Y is the one point computation of X by the definition of this. Okay, so this is a theorem. So basically, what one point compactification means? So I mean, suppose you have some circular arc like this, but it is not totally connected. I mean, but it is not properly connected. There is one. I mean, the some one point is missing there. Okay, so obviously this is not compact, right? So by one point compactification, we mean we will add one point, some point, and put it here so that we, after adding the new space will be compact. Okay, this is the main idea of one-way compactification. So basically, one-way compactification means you have some non-compact space, and then you add some point with that space, and within certain conditions, that space becomes compact. So that's why it is compactification, and since it has been done by adding one point, that's why it is one point compactification. So this is the, I mean, you can say this is the intuitive feeling of this one-way compactification. Okay. So can you tell me what is one point compactification of R? Suppose this real life. What maybe it's one point compactification? Can you guess? I mean, suppose first real line is not compact. Okay. And anyway, real line can be thought as an open interval, right? Now observe that this open interval and this thing are same, correct? Now can you please guess what is the one point compactification of real line? I mean, so or basically you can say that what is the one point compactification of this space? That you can add one space and it will be some new compact space. What will be this? Can you please guess? Intuitively, of course.
Sir, can be written as a union of intervals, open intervals.
Okay, can I put it? Sorry.
So, open intervals, the adding of endpoints,
Mhm.
and R is a written as a union of the all the open intervals. So, if add the endpoints each interval,
Yes.
then R becomes compact,
Then R becomes.
compact.
So you have said that R can be written as disjoint open intervals, right? And
Yes, yes,
then you, I mean, you join these gaps, right? Correct.
yes,
Okay. But the point is that if you want to join these gaps, you need to put, I mean, you need to put each point for each gap, right? Then it will be not one point compactification, correct? If one point compactification, you need to make it compact by adding only one point, right?
yes, yes, yes,
So, so this, I mean, your way is correct, but it is not one point compactification. So, I mean, you can think this as follows. So, the real line R, you can consider it as open interval, right? Okay. Now, open interval can be thought as this. I mean, yeah, these are. I mean, this thing and this open interval are same, right? Correct. Now,
yes, sir.
yes. Now, if you add one point here, then it will be what? Circle, and which is compact, right? So that's why the one point compactification of R is circle. So I mean, so this is the one example actually. So do you understand the example or any confusion? Please ask.
Sir, the open interval which we are taking, it is the whole of the real line.
No, no, I mean the real line and the open interval 0, 1 are homeomorphic, right? Correct. So instead of working with real line, we can think it as open interval 0, 1, right? I mean, we want only the finiteness of this thing. That is, we choose a finite open interval. Understand?
Yes, sir.
So yeah, so this is the one by compactification of R, which is circle. So that's the point. Okay, so one thing is that okay, I mean this is the intuitive guess, but rigorously we need to prove this one point compactification of real and a circle. But this case telling that what is the possibility. Okay, so okay, we will come to that soon. Okay, so first solve some problems. Okay, show that Q not locally compact. So that Q is not locally compact. It can be proved by just using definition. Just think about it, take your time. You only need to use the definition, nothing more than that.
we consider as a subspace of R?
Uh, sorry, what? Yes, question properly.
Subspace of R when each rational point
Yes.
is opening Q singleton. If it is as a subspace topology,
Yes, this is Southwest topology. Then what the say?
uh, if we consider it is a subspace of R, so if we take any rational points, so then open interval in R intersect with Q.
Yes.
So every singleton set in Q, it is an open.
No, no. What you need to check? You need to check that open interval AB intersection Q, which is open in Q. This cannot be inside any compact subspace of Q, right? This is what you need to check, correct? Am I
Yes, sir.
right?
Yes, sir.
I mean, yeah. This is what you need to check. That's the point. Okay. Just try to use the either sequential criteria or you can try to use the sequential criteria here. Okay, and also you can use the fact that between any two rationals they are always irrational. The denseness you can use here. Okay, that's the only way you have to use. Try to solve it.
Now, if we thus enumerate the points between AB of all rational number R1, R2, Rk, so we get a sequence Rk.
Yes, the thing is, you are using sequence, right? So you need to use choose something such that the sequence converges, right? So that you can use the compactness of the set capital K, right? You understand the point?
Yes, sir.
A is compact, so you need to use somehow. So you need to choose a sequence which converges at least. Okay? Then only we can make any some argument, right? So think about in that. Okay. So yeah. So the thing is, choose an choose an irrational number
Yes, sir.
from
Root 2
open interval.
plus
Yes. So, yes. What?
Root 2 minus 1 by n root 2 plus.
No, no. Suddenly what root? Suddenly from where root 2 minus 1 by root 2 plus 1 by n?
Sir, open interval. Open interval.
No, no. You need to check that any type of open set cannot be contained in the compact set, right? It is any open set. You can't start with some particularly chosen open set, right? It has to be any.
Yes, sir.
Correct. So x is an irrational number between open interval AB, right? So obviously, so we can get a sequence xk inside AB, sequence of rationals, such that this xk converges to x, right? Now everything is contained inside capital K, okay, and AB is also subset of capital K. So now, I mean, since this xk is contained inside capital K and capital K is compact, so that x has to lie inside capital K, right? Correct. But capital K is subset of Q, but x is chosen to be irrational. So that's the contradiction. Do you understand? I mean, first,
Yes, sir. But
yes.
sir, but how we conclude that xk must converge to be that x?
No, no. I mean, the thing is, we have chosen an irrational number from open interval AB. Okay. Now, by density property, we will get a sequence xk of rationals inside open interval AB, such that that sequence converges to small x, right? Do you understand the point?
Yes, sir. Okay.
Yes. So x has to belong to K due to compactness of capital K. This is the contradiction. So that's the full argument. Is it clear?
Yes, sir.
Okay. Now, okay. Now show that one point compactification of R is this. Okay. So previously we have proved it using some vague idea, but we now need to prove it reversely. Okay. Okay. So before starting this, what we need to do? This is the first thing. Okay. We need to somehow show that S1 contains capital R. Also, I mean S1 compact house drop. This is obvious, right? I mean this is true, right? And also R, sorry, S1 minus R is a single concept, right? This is what we need to show, correct? By the definition of the one-point compactification, right?
Yes. Sir, uniqueness.
Sorry, can you please repeat?
Uniqueness.
Sorry, I didn't repeat.
Sir, that one point compact, it must be unique.
Yes, yes, it must be unique, right? So if we show that something will, I mean, if we show something like this, then we are done, correct? But the thing is, S1 cannot be, I mean, S1 is a subset, S1 contains are that is not possible directly, right? So for this, we need to use some kind of trick, okay? So, I mean, we need to construct a function f, I mean, need to construct a function f from what to where, from S to R to S1, such that if R is homeomorphic to R and the following condition holds. S1 contains f of R and S1 minus f of R is a single term set, right? I mean, this is what we actually need to do. So we need to find a function f from R to S1 so that f of R and R are homeomorphic and S1 contains f of R, okay? So I mean, so basically in this line, instead of r, we need to do it for f of r. Okay, this is the first trick. Okay, so now try to construct a function which satisfies these following properties. Now try to construct. Okay, think about it. I mean, do you know the what is the one? Yeah, do you know stable projection?
No, sir.
Yeah, so if you, I mean, so what is the stable projection? So stable projection was, so you consider the full circle minus the top point, and the map was that if we take any point on the circle and yeah, and consider this remote point and add this 2 point and extend it, and where it will intersect the line, that is the image of that function. Okay, so I mean, just you can read the store projection. This will tell that fr, under the store projection, fr is homeomorphic to r and s1 contains f1. Okay, so that's why the one-way compactification of real line is circle. Do you understand the argument? I mean, the argument you understand.
Sir, basically we map the points of the circle on the real line.
Yes, yes, correct. Okay, now, okay, in so as we have seen in the case of compactness, connectedness, the continuous image of compact matrix is connected. Okay, but in locally compactness, such a thing is not true. So for this, first give a counter example. I mean, for locally compact situation, this is not true, but try to give a counter example. For this, you can use this example that rationals is not locally compact. You can use this. I mean, you can use this for constructing this counter example, right?
Sir, if we
Yes.
define a map from R to R, is that each irrational points map to be zero?
What you take it as a
R, set of R,
okay, and y.
at the same R.
Okay, use your both with usual topology, right?
Yes, sir.
So now give tell me the map.
Sir, the rational points map to be zero,
Okay,
and irrational points such as if it is enumerated by R1, R2 dash dash, then it is itself RK.
national point goes to zero, right? Correct.
Yes, sir.
An irrational point are I mean irrational set how we can enumerate it is uncountable, right?
No, sir. Irrationals are goes to be zero and rationals are goes to be itself.
Rational goes to be itself and irrational goes to be zero, right?
Yes, sir.
So now firstly observe that this function is not continuous.
Yes, sir.
I mean
Only zero.
it is a continuous function, right? Correct.
Yes, sir.
So try to think about continuous function. Okay, so okay, I mean take x to be q to the discrete topology and y to be q with usual topology. Okay, and from x to y take the identity map, and of course y is usual topology. I mean a q with usual topology is y is not locally compact. We have seen it before. And x with x means q with discrete topology is compact, right? So I mean this is the counter example. Understand?
Yes, sir.
Okay. But the thing is, um, mm, but if x to y continuous plus open, then x locally compact implies fx locally compact. I mean, so the here the condition openness of f is necessary for the x locally compact implies fx locally compact. Okay, so that's the thing. Now try to do this. If continuous open, then x locally compact implies fx locally compact. I mean, just go with the definition. You will get the try to write the solution. I mean, try to think about the solution and let me know.
if we take a point y, which is fx is equal to y, and vy is a neighborhood open set around y. So since the map is continuous, so the inverse image of a vy is an open containing the point x, and x is a locally compact. So we find a compact neighborhood around x. So that
Yes.
x belongs to the k. K is contained in f inverse of a vy.
Yes. Correct. Right. Perfect.
So f of x belongs to the f of k, and which is contained in vy.
Yes.
Since k is
That and
compact,
perfect. Perfect.
okay, sir.
I understand. So now, okay. So you know the countability. You know the first countable and second countable spaces, right?
Yes, sir.
Do you have any doubts from this question or any things that you did not understand in the lecture notes or anything from assignment? Any doubt? I mean, not this question, I mean, from other question also. Any doubt?
Sir, मतलब compactly generated space.
Okay. Okay. I need to make this thing different. Compact general space. And except that,
Uh,
sorry.
no, sir. Sir, I did not understand this thing. But
Oh, which space? Which space? Sorry.
compactly generated space.
Yes, yes, that I understand. I need to prepare it and I will tell in the next live session. Except that, except that, okay. So, um, so, do you know Lindelof space? I mean, so you know the second countable space, right? So also you know that second countable space implies Lindelof and separable, correct? Right?
Yes, sir.
Okay. So, um, do you know that product of Lindelof is Lindelof or not?
No, sir.
Okay, so basically the product of Lindelof space, not Lindelof. There is a thing. It is a fact. Okay, I mean it is not in general true. I mean it is a you need to provide a counter example. Okay. So the okay. So first try to think about. I mean think with RL. Okay. Think with RL. Use this thing. RL is Lindelof itself, but RL2 not Lindelof. Now try to think that why RL2 is not Lindelof. Take your time. Okay, you think about it. I will back up. হ্যালো, কে কে বলছেন? জুতোর বাড়ি খাবি? বল, কিছু না বল, কিছু না বল বল। ছাড়, এখন ওটার পিছনে পড়ে লাভ নেই, তো বল বক্তব্যটা। হ্যাঁ 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 হ্যাঁ, ওখানে প্রজেক্ট করছে, ওখানেও প্রজেক্ট করছে তো। আমার ইনফরমেশন থাকে বলেছে। দেখ, সেটা বড় কথা, আমি কি করে জানলাম সেটা, ওটা বড় কোশ্চেন না। এরকম ভাবে না, ওকে জিজ্ঞাসা করে জেনেছি। আরে আমার ওখানে অলরেডি চেনা জানা লোকজন আছে, মানে ওটা চেনেছি সেটা না, আমি অন্য কারোর কাছে কথা জানতে পেরে গেছি, এটা হচ্ছে বিষয়। দেখ, সেটা পয়েন্ট নাই, পয়েন্টটা হচ্ছে যে তোর ওসব দিকে মাথা খাবে লাভ নাই। তোর টার্গেট হচ্ছে ভালোভাবে পড়ে নেট। কি বললো? এই কামন, আই মিন, তোকে নেট ক্লিয়ার করতে হবে, নেট গেট আর ইংলিশ তিনের মধ্যে একটা ক্লিয়ার করতে হবে, রাইট? সেটা অনেক বেশি ইম্পর্টেন্ট, কথা মাথায় থাকে। আই মিন, ও যে ইন্ডিয়া যদি করতে আলাদা হয়েছে না, ও যে ইন্ডিয়া, ও যে অ্যাব্রোডে পিএইচডি করে, সেটা তার জন্য কোনো সমস্যা নেই, কিন্তু এখানে পিএইচডি করবে আশা করি, ওকে? তো সেই ক্ষেত্রে তোকে সেই মতো করে ভাবতে মাথায় এগুলো। তো কি করছে ওইভাবে কাজে নেই। তোকে নেট গেট ইংলিশটা এখানে ক্লিয়ার করতে হবে, ওকে? অ্যাজ লং অ্যাজ তুই অ্যাটলিস্ট একটা ক্লিয়ার করতে হবে, না হলে কোনো লাভ নেই। এটা হচ্ছে মোদ্দা কথা, আমাদের এগুলো কথাটা মাথায় ঢোকা, বুঝলি? মাথায় ঢুকলো? কনফিউশনে থাকিস না, কনফিউশনে থাকিস না, কনফিউশনে থাকবি না, যে কোনো একটা। হুম, হুম। এই কাম অন, এক সেকেন্ড, এক সেকেন্ড, কাম অন, আই মিন, অন্য দেশে থেকে 1,22,000 দেখে না, ও যেই দেশে থাকে সেই দেশের রেসপেক্টে 1,22,000, ওই দেশের কতটা সেটা, সেটা তাকে জিজ্ঞাসা করতে হবে, ওকে? এরকম ভাবার লাভ না। হুম, আরে বল। হুম, হ্যাঁ, সরকার মাত্র। তাহলে লাভ কি হলো? তো তোর টাকাটা শেষ হয়ে গেল, আর কিছুই থাকছে না ডেলি, রাইট? তোর 1 মিনিট, তুই বাইরে কারণ যেতে চাস, তুই কিছু টাকা হবে, যদি সেটা হয় তাহলে আলাদা বিষয়। হ্যাঁ, যেটা যেটা হবে না সেটা ভেবে লাভ নাই, তাই যেটা যেটা সম্ভব সেটা তো ভাবতে হবে। না, ওরকম যেতে চাই বললে হবে না, মানে সবকিছু সবার হাতে থাকে না, কথাটা মাথায় থাকে, যেন যেটা সম্ভব নয় সেটা ভেবে লাভ নাই। না, সেরকম নাই, বাট বল। না না, বক্তব্যটা সেটা না, বক্তব্যটা হচ্ছে লজিক্যাল। তুই জানিস তুই যেতে পারবি না, বা তুই যেতে চাস না, অনেক কারণে যাওয়া হবে না, দ্যাটস এভারিথিং, বাট যখন যাওয়া হবে না তো ওটা ভেবে লাভ নেই, রাইট? আই মিন টু সে, দুটো একসাথে ভাবা সম্ভব নয়, আমি এটাই বলতে চাইছি, দুই দুই নৌকা পা দিলে মুশকিল আছে, বুঝলি? আমাদের এগুলো, না, এটাই তো বক্তব্য আমাদের এগুলো। না, ওর গাইড কি আমি সেটা আমার আইডিয়া নেই, কোন আইডিয়া নেই গাইড, আমি জিজ্ঞাসা করিনি কোনো। কেমন, তোকে একটা রমেশ স্যার একটা কথা বলেছিল না, যে ভালো হোক খারাপ হোক বাইরে চান্স পাবো অনেক বেটার। একদিন রমেশ স্যার ক্লাসে কথাটা বলেছিলাম, যতটা মনে আছে, ফাংশন ক্লাসে, রাইট? এবং কাউকে এটা বলেছিল কথাটা, আমি শুনেছি, আমার ঠিক মনে আসছে না কিছু। বাট পয়েন্টটা হচ্ছে, নট অনলি মানে বাইরে চান্স পাওয়াটা এনিওয়ে সবসময় বেটার, যদি মোটামুটি কলেজ পাই সেটা অনেক বেটার, এটা হচ্ছে বিষয় ইন রিয়ালিটি, ওকে? এবার কেন সেটা তোকে আমি বাইরে, সেটা আমি মেসে গিয়ে বলছি, সরি হোস্টেলে গিয়ে বলছি। এটা হচ্ছে বক্তব্য, ঠিক আছে? তোকে আমি হোস্টেলে গিয়ে, আমি হোস্টেলে 10 তারিখে পৌঁছাবো, 10 তারিখে বলছি, ঠিক আছে? ঠিক আছে? কি? দাঁড়া দাঁড়া, 1 মিনিট দাঁড়া, 1 সেকেন্ড, আমি হোস্টেল 10 টায় পৌঁছাবো, তখন গিয়ে বলছি, ঠিক আছে? বুঝলি, আমি ক্যাম্পাসে নাকি আমাদের বাইরে আছি, ঠিক আছে? মানে এগুলো So, do you get that why RL2 is not lambda? Any idea you got? Any idea?
No, sir.
Okay. So it's a quite tricky problem actually. Uh, okay. So basically, first we will check. I mean, first consider the subspace L x comma minus x. Okay. First thing is this subspace L is closed in RL. Okay. I mean, this is we will prove, but first let me tell the sketch of the proof. Okay, this is the first thing. Now observe some things that so what this sounds will L will look like. L will look like this x comma minus x line, correct?
Uh, sir, sir, L is open interval x minus x.
No, it is not open interval. It is a just I mean it is just coordinate L x comma x. I
Oh,
mean
okay.
yeah. So this is the subspace L, correct? Now uh now suppose if RL2 Lindelof, okay. Now since L closed, so RL2 minus L it is open, right? Now choose any point x comma minus x inside L. Now in RL2, what are the basis elements? The base elements will be of the form like this. So in RL2, this type of thing are the basis elements, right?
Yes, sir.
So these are all possible base elements for A, D values over R. Okay, and these all possible basis elements covers L also, correct? I mean, this thing covers L, right? I mean, because each of this type of set contains the point x comma minus x, and x comma minus x is point of L, right? So this type of
Yes,
so contains it. Now if RL2 is Lindelof, then this must have countable subcohort, right? But then this implies what? This implies the countable subcollection of this thing covers L, right? I mean, if RL is Lindelof, then it must be countable subcover. So L must lie inside this portion. So this, I mean, we'll get a countable subcore of this portion which covers L, right? But observe that this third bracket x comma a cross minus x comma d. This type of open intervals um, intersect the line capital L only at one point, right? Correct? Do you understand? I mean, what we get? We get that this type of open intervals covers L. Okay. Now, this type of open intervals intersect the line capital L at exactly only one point, right?
yes,
So, if only countable subcollection of this open intervals covers the whole L, then I mean this is not possible because each of this element intersects L at one point, and the line L itself has uncountably many points, right? So this open cover can't have a countable subcover. Okay, do you understand the argument?
sir. Last repeat.
Yes, yes. So I mean, so if RL2 is Lindelof, then this open cover is countable subcover. Okay. Now, one now only this portion will contain the line capital L, right? So this portion will have a countable subcollection. Okay. which contains capital L. Now observe that each of these states x comma a cross x comma minus d, each of these uh, open subspaces like this intersects the line capital L at exactly one point, right? Correct. So if the only countable subcollection of those open sets contain L, then L will have a finite. No, I mean L will have a finite. I mean the L will be finite set, right? Sorry, countable set. But L is itself uncountable set. So I mean the point is each of these open interval intersects L at only one point, but L has uncountable number of points. So only countable number of this portion can't cover the whole line L. So this is the argument. Do you understand?
Yes, sir. Sir, basically, we are saying that the intersection of the points on the line. So,
Yes, yes. Can you please repeat?
sir, the contradiction what we have,
Yes, the
the
contraction is
only
that the intersection of the point. I mean the each of these open sets x comma a cross third bracket minus x comma d intersects the line L at exactly one point. So if countable, so I mean if we have a countable subcover, so we only have a countably many open intervals, sorry, open sets, and each of these countably many open sets intersect L at exactly one point. So this tells what? This tells that L has countable number of points, but that is not the case, right?
yes, sir. Okay, sir.
So this is the argument. You understand?
Yes, sir.
Okay. So the product of Lindelof may not be Lindelof. So what about the subspaces? So in general, also subspace of Lindelof need not be Lindelof. Okay. So can you give some exact counter example? The subspace of Lindelof is not Lindelof. It's a counter example.
Sir, the line which we defined in the previous example.
Yes. Then I mean in the previous example, the RL2 is not Lindelof, right? But here you need to show the subspace of Lindelof need not to be Lindelof. So you need to find a big space which is Lindelof first, right? So the previous example will not work here, correct?
Okay. Sir, if we take the interval AB, closed and open interval, and A, A,
you are you talking about this? Are you talking about this?
Uh, yes, sir. I'm taking, yeah, but B is open. RL element.
The open right side. Okay. Okay. So
Yes.
okay. And then okay then
Sir, then the cover is defined as the closed A and open B plus 1 by N.
okay. Okay. Now you are claiming that this has no countable circular, right?
Yes, sir.
Firstly, this I mean this is the countable circle because n I mean the set of natural number is countable, right? So this cover is already a countable cover. Okay. So I mean that's the point. So this example will not work this time.
Yes, sir.
Yeah, try to make some different examples. I shall get back to 2 minutes. So do you get any counter example?
No, sir.
Okay. So the counter is as follows. Do you know the ordered square?
Sir, in which we define partial ordered relation.
Yes, yes, right. So, I mean, on the I cross side, the dictionary, the order topology. I mean, the yes, that you have said the dictionary topology. With respect to topology, the space I just call it ordered square. Another thing is, ordered square is compact. Do you know this? Do you know this? That ordered square is compact or not?
No, sir.
Okay. So, I mean, it's a fact that it's a theorem that if X is an ordered set with order topology and X has a UV property, then any closed interval of X is compact. So this is a fact, okay. So now using this fact, I0 square is compact, okay. Now the thing is, you should read this theorem and try to understand the proof also, okay. And if you got stuck this proof already, please ask me in the next live session, okay. But it's a very important theorem, so you should not, I mean, no one should skip this theorem, okay. So using this we can get that I0 square is compact first of all, okay. Now so compact, so it is obviously linear, right? Now the thing is, consider the subspace A of uh, I cross open interval 0 1, okay. And consider the open interval, consider the open cover single x cross open interval 0 1. So what is this? So this A is basically this thing, I cross 0 single x, x cross open interval 0 1. These are the open covers we are taking, okay. And x belongs to 0 1, third vector 0 1. So this is then collection UX in open cover of I space. It is obvious, right? Now it can't have countable sum. Why? Because since, I mean, observe that. So I mean, these open intervals are disjoint, right? Sorry, these open intervals are disjoint, right? So if this has countable subcovers, so only countably many open intervals need to cover this whole I cross open interval 0 1, right? But this is not possible, correct? Understand? I mean, there are uncountable many points, so only countable thing can't cover the uncountable portions, right? Or you can think it like as um, ux intersects the line I only singleton x, okay. So now if only countable, now if only countable ux's covers I0 square, then the baseline I cross 0 1 will be countable. this line intersect the baseline only exactly one point. But that is not possible, right? So that's why the collection effects can't have countable subcover. You understand the point?
Uh, Sir, but the space which we have taken, I cross and M01, so it is a subspace of RL.
No, no, it is not. It is subspace of I0 square.
Okay, okay. So, but we need to find the subspace of RL which is not named enough.
Yeah, it in real situation. I mean, in real line, it is not possible because um, in real line, it is a fact that if a space is Lindelof, then its subspace is also Lindelof. Okay. I mean, in real line, in good spaces, this is not possible. So that's why these counter examples are quite tricky.
Okay, sir.
Okay, so you have seen. So we have seen what we have seen two things. That product of Lindelof may not be Lindelof, and subspace of Lindelof may not be Lindelof. Okay, but under certain condition, product of Lindelof space may be Lindelof. I mean, has to be Lindelof. So first is that X Lindelof and Y compact. This implies X cross Y Lindelof. Okay. Compactness, one is Lindelof and another compact. This together implies product is Lindelof. So try to prove this. In order to prove this, you need to use the tube lemma. So try to think about it, try to solve this. You can take your time.
Sir, if we supposing that suppose U alpha is an cover of X cross Y. So, since it is an open, by tube lemma, we take a point x cross y such that uh, the neighborhood of x cross y is contained in that open set, and which is a true for each alpha.
Okay. No, no,
So, and
no, no. The thing is, not for each alpha, for some alpha, right?
yes, sir, I'm doing
Then, then,
since y is lambda log,
no, no. Y is not Y. X is length, right?
sorry, x is lambda. So the point x is covered by countably many subcover.
Yes. No, no. Firstly, U alpha is open cover of X cross Y, right? It
Yes,
is not a cover of X. So how will get the subcover of X? I mean, the cover of X will give the subcover, but how the cover of X cross Y will give the subcover of X?
uh, sir, the open set which contains x, suppose it is a v cross y. So by tube lemma it is contained in ux,
Yes.
and if containing the point x cross y.
Then,
Sir, it is a true for each point of x.
sorry, can you just repeat?
Sir, this is a true for each point of x.
Yes, correct. Then,
Sir, I did not get any idea.
you are almost there. I mean, you have used tube lemma, right? So means you have already used the compactness of Y, correct? Now you need to use the Lindelof-ness. Just think about it. I mean, you are there already.
Sir, firstly,
Please be louder.
okay. So, sir, the set V, which is around x, and we can say about for every x.
Yes, correct.
So, if we take union,
Yes, so those, I mean, so that's the Vx. I mean, if you call it Vx, is an open cover of X, right? Correct. So it will have a countable subcover Vxi, I is equal to 1 to infinity. Okay. So obviously, then x cross y is equal to union I is equal to 1 to infinity Vx I cross y, which is nothing but union I is equal to 1 to infinity uxi. And each uxi is an, by construction, each uxi is an finite union of the of u alphas. So it is, as a whole, it is countable. I mean, those collections of uxi is countable, so that's why u alphas have a you are for this collection you have the counters of covered for X first, right? So yeah, very good. So I mean, the whole argument you understand. The last question.
Yes, sir.
So, so also falling from. Suppose if X has countable dense subset, then every collection of disjoint separated in X is countable. So the question is that if X has a countable dense subspace, then every collection of disjoint open sets in X is countable. So yeah, so try to do this. I mean it's a problem, but try to do this.
Uh, Sir, since X is a countable dense subset,
Yes,
so if A is a dense in X, so it intersect every open set U alpha,
yes, correct.
and so if we define a map from A to for each U alpha,
Yes,
if we prove it like in surjective, the countability examines.
no, no, subjective. I mean, how you can get a map? The countable depth, we have only a subset, right? So, I mean, how you get the map? I don't get it. I mean, how you get some map here? Hmm?
Sir, because it intersect U alpha,
Yes.
A intersect U alpha.
So I mean, how you get the map? I don't get the picture. I mean, how you get some map here?
Uh, no, sir. If we take a map from the index set where we indexing the U alpha
Yes.
to U alpha, and if we define I,
No, no, don't think of map. Just use the definition and use the definition of denseness, scale count, etc. I mean, the maps are not coming in this picture. I mean, no need to use maps unnecessarily. Okay. You have a countable dense subset. I check that you can have only countably many disjoint open sets. That's the only thing you need to use. Right? Correct? So the thing is, I mean, suppose we have an, I mean, so we have some U alphas, disjoint open intervals, right? Now, DB countervalence. So U alpha intersection they non-empty for all alpha. Okay. So choose each element A alpha belongs to U alpha intersection D. Then this subspace A alpha is contained inside D, right? Now since the collection U alpha is, I mean, if the collection U alpha is uncountable, then the collection of those A alphas are also uncountable, which contradicts the fact that D is countable. So the collection U alphas has to be countable, right? So this argument, understand?
Sir, but A alpha is a one element. So how it is implied? Sir, A alpha is a some element.
Yes, right.
So how it is implies that if it is in D, so U alpha must be counted.
Yes. So the thing is, I mean, we are choosing A alpha from each U alpha intersection D, right? And since U alpha the collection is disjoint collection, so A alpha not equal to A beta for all alpha not equal to beta, right? Correct?
Yes, sir.
So inside the we got a, I mean inside the we got the collection of those one A alphas which lies inside D, and for each alpha not equal to beta, A alpha and A beta are not equal. But there are if we assume that there are uncountably many U alphas, and we are taking A alpha for each A alpha U alpha, then we will get uncountably many A alpha, right? So that's why the collection A alpha will be uncountable if the collection U alpha is uncountable. So that's the so that gives the contradiction the fact that D is countable. Understand? You understand?
Sir, the collection A alpha,
Yes.
it is all the distinct points of U alpha, all the set collection of distinct points,
Yes, right.
and it is contain it is all these points of U alpha.
Yes. Because the U alpha, because D is dense and U alpha is open, so dense means what? It intersects every open set. So that's why U alpha intersection D is non-empty. And so we can choose a point A alpha from U alpha intersection D, right?
Okay, sir.
You understand?
Yes, sir.
Okay. Okay, so we have done one counter example that subspace of Lindell may not be Lindell. Okay. Now, it is true if we impose a condition. Show that closed subspace of Lindelof space is Lindell. So this is the thing you need to check. Closed subspace of the Lindelof space is Lindelof. Try to do it. I mean, it can be done by using definition. Okay, let's solve.
Sir, suppose U alpha is an open cover of Y.
Yes.
So, where each of U alpha is open in X, so U alpha intersection of X is open in Y. Yes, sir, I'm trying.
Be louder.
Yes, sir, I'm trying after that.
Yes, please try.
So if we write as a Y is in union of a U alpha intersection X. Uh, So X is a
Please repeat, please repeat.
sir. So Y is in union of a U alpha intersection X and alpha value of index set. Since X is a Lindelof,
Yes,
so if then X is also contained in that union of U alpha. So X intersection of a U alpha.
yes.
So then we because X is contained in countable in any subcover, so if you intersect X with X, so it becomes a countable union of
Okay, now, okay. Now the argument is follows. If U alpha is the open set of X, okay, then this collection U alphas union Y minus X is a cover of Y, correct? Because Y minus X is open, right?
yes, sir.
Now Y is bundled up, so with the countable subcollection U alpha I is equal to 1 to infinity, union Y minus X, this covers Y. So obviously X is this portion, correct? So this is the argument, understand?
Yes, sir.
Yeah. So okay, so you know the regularity, normality, I mean by what this means, you know this, right?
Yes, sir.
Okay, so can you please give the definition of regularity?
Sir, in which the single points and the closed set both which contains not that point, it is separated by open set, disjoint open set.
And do you know the fact that uh, R with K topology, RK is not regular? doing this.
Proof, proof no.
Sorry.
Sir, proof, how to prove? I don't.
Okay, so let's go. The thing is, R is K topology, not regular. I mean, have you seen the proof? Have you seen the proof?
Uh, yes, sir, in my MSc.
So basically, we show that RK is not regular. Okay. So this means we will take a point and a closed set which does not contain that point and show that we can't get any open intervals containing that with a discharge. So firstly, we need to choose the point and we will choose the closed set. So we are taking the K 1 by n. The flow is the closed inside RK. Okay. And uh, the set 0. Okay. And 0 does not use a capital K, correct? Now we will show that there does not exist any open set U containing 0 and open set V containing K so that the intersection is empty. This is what we will show. Okay. So uh, so assume that there is open interval U containing 0 and V containing K so that U intersection is empty. Okay. Now use an open set containing 0. So there is an open interval of this form this subset of U or this subset of U, correct? Either open AB subset of U or an open AB minus K subset of U, right? Now if open interval AB subset of U, then these open intervals AB contain some point of K, so which contradicts the fact that intersection is empty. So only the only the base element containing 0 will be of the form this. This is the first observation. And the second observation is that since V is an open set containing K, so the any open set of P containing K will be of the form only open interval C, right? Now, so suppose this is open interval AB and suppose this is open interval C. Now choose a point 1 by n between these portions. Okay, and then now then the point 1 by n plus 1 either it will lie left side of C or it may lie uh, right side of C. Okay, but whatever the case is, if we took any point which lie inside 1 by n comma n, this point, if you call it Z, this point belongs to open interval AB minus n, and also this point belongs to CD, correct? So I mean, so in that case, Z belongs to U and Z belongs to P. So U and V can't be non-empty. So I mean, so the intersection can't be non-empty. So that's the thing. Do you understand the argument?
Sir,
Oh, sorry.
yes, sir.
Oh. Okay, just since it's done almost. So just you can look at the chat box. There is a Google form link I have shared. Please mark your attendance by submitting the Google form.
Yes, sir, I did.
Okay, so do you have any questions from any of the sessions, any doubt or anything you want to ask?
No, sir.
Okay.
Okay, sir. Thank you, sir.
Yeah, so if you have any doubt, you can ask me the question. Okay, I'm ending the call.